Hi, this is Chapter 13, Kinetic Theory, Part 3 for Physics 1. We left off looking at the ideal gas law, and we had looked at previously PV equals nRT, and R could be either 8.314 or 0.0821, depending on your units. Okay, now the next thing we're going to look at is the ideal gas law with molecules. And so there's a couple of things we're going to get into. One, capital N is considered the number of molecules. And capital N equals N, which is the number of moles, times Na, which we call Avogadro's number. And this is equal to, let me just kind of actually define this off to the side here. Na is equal to 6.02 times 10 to the 23rd molecules per mole. Okay, so if we have the number of moles, we can multiply it by this big number and we get the number of molecules. So if we have one part of this, we can't always switch it to the number of particles. Right. Now we also have another constant involved because we can't use R as the constant. And so this R, if we take, and I'll write this out, we're going to let K equal that R constant over Avogadro's number. So this is 8.314 joules over mole Kelvin divided by 6.02 times 10 to the 23rd molecules over moles. And we get a number of 1.38 times 10 to the negative 23rd joules, that's come from this, per molecule Kelvin. This is called Boltzmann constant, and it will come up a few times. So it's another constant. Now the good thing with this ideal formula, PV equals NKT, is you can easily get the number of particles if you have the number of moles. You only have one constant to deal with, and that is this constant. Right? So it's not in question of which one you're really dealing with. But it does kind of force you to have to use the right kinds of pressure and temperature. Alright, so let's say we have a volume of gas at what we call STP, and it's in a container that it contains 3.5 times 10 to the 23rd molecules. So this is N. Or 25th molecule, sorry. Okay, STP. I'm going to go down to what that is involved with. STP stands for standard temperature and pressure. Okay, for standard temperature, your temperature is equal to 273 Kelvin. That's considered the standard, which is technically 0 degrees Celsius. For pressure, your pressure is going to be either 1.01 times 10 to the 5th pascals, or it would be 1 atm. Okay, and so you have two different pressures depending on your units, but this is going to be the kind of pressure you will use, alright, for standard pressure and temperature. So because we're dealing with joules here, we're going to do 1.01 times 10 to the 5th Pascal as the standard pressure. And so we do PV equals NKT. We are wanting the volume, right? In this formula? Yeah, we're finding the volume. So volume equals N capital N KT over the pressure. So N is 3.5 times 10 to the 25th. K is 1.38 times 10 to the negative 23rd. I'm running out of room here. Temperature is, well, put up here, is the 273. And then over the pressure, which is 1.01 times 10 to the 5th Pascal. Alright, so 3, yeah, it doesn't work with the pen. Right, 3.5 times 10 to the 25th times 1.38 times 10 to negative 23rd, and divide times this by 273. Almost forgot that thing because I had it right off to the side. And then divide that by 1.01 times 10 to the 5th. And we get 1.31. And since we're dealing with pascals, we're getting meters cubed. Right, so I kind of try to outline this out if we are dealing with, and it works for either one of these equations, but when we're looking at standard temperature and pressure, if you have pascals, you're going to end up with meters cubed. If you have ATMs, you're going to end up with liters, since that's what you end up with. The two are basically linked. With standard temperature and pressure, you won't have it. There was no standard value. Just the standard pressure and temperature. So for the gas constants, to use the one that has joules, you need meters cubed and pascals for pressure. And to use the one that's liters, ATMs, you need liters and ATMs, which is easier to remember. So that's just like a helpful table to try to get your head wrapped around it. Okay, so now we're going to get all into this kinetic theory. And we got some postulates here, which postulates are things that actually haven't been proven, and it's things we kind of assuming in a sense to be true. So one is there are a large number of molecules within a gas, and each molecule has a mass m. They move in random directions. They have a variety of speeds, and a gas will fill its container. Right, so wherever the container is, the gas is going to fill it. They're going to be moving at random speeds, which is why we have to look at the average speed. And they're going to be moving in all random directions, and they're going to each have their own mass. Well, each type of molecule has its own mass. Right, the molecules are far apart from one another, and what that means by far apart is that the separation is greater than the diameter. So they're a lot farther away than the size of themselves. The molecules obey the classic laws of mechanics, which means conservation of momentum, conservation of energy, forces, that all those laws and rules. There are attractive forces between the molecules. The potential energy created from the attractive forces is small compared to the kinetic energy of the molecules. Right? So what these two mean is basically that kinetic energy is what's keeping them apart. They're moving so much faster that they're able to stay apart from one another. If they slow down, they start to become more attractive. By slowing down, they're able to start to bond to one another and become more attached to one another because of the attractive forces between them, which makes sense because as they slow down, they connect, form a surface, and become a liquid, and then eventually they will connect enough with bonds to become a solid. And that's because these attractive forces have then started to outdo this kinetic energy, because the kinetic energy is now low, thus they're not moving as fast. Alright, so the collisions are perfectly elastic, which means no loss of energy. So as they collide with each other, they bounce around, and there's no heat transfer between one and the other. Alright, so this next thing I want you to really remember, because I'm going to throw it into the next chapter, and you may be like, where did that come from? Well, this is where it's coming from. This average kinetic energy depends over here. The average kinetic energy deals with the fact that you have an average speed for this for all the molecules. Okay, there's an average speed which will cause it to have an average kinetic energy. And we can also look at this average speed as what we call the root mean square. So it's the square root of the average of speed squared, which you see down here. This 1/2 mv squared is equal to 3/2 kT. Well, K here is Boltzmann constant that we just covered, which is equal to 1.38 times 10 to the negative 23rd. Right, and so what we have here is this average kinetic energy is directly proportional to the temperature. So if you measure the temperature, you have an idea of the average kinetic energy as well. Right, so when we have these gases in these containers and they're moving around, you'll have different speeds for each molecule, and this is a graph of the different speeds and how they're found. So where it becomes a hump, this is going to be where the highest amount of particles are at that speed. And so most particles for this purple one, which is like xenon, is at the speed that's about, I don't know, see, that's 5, 4, 3, 2, maybe 2. Yeah, about 200 meters per second. Whereas this blue one, which is helium, the average speed is going to be about 1100 meters per second. That's because most of the particles are around this point. Alright, so we know now all the speeds in the gases are the same temperature. So there is a variation. Some are greater than the average, some are less than the average. And so this gas kind of will show how most of them do fall close to the average, but there are also those outliers. And so if we were to take this and we were to solve this for v squared, so the 2's cancel out, so you get mv squared, I'm going to drop that bar off right now, equals 3 kT, and divide the m over, so you get 3 kT over m, and take the square root, and so you get square root of 3 kT over m. And so this is your root mean squared, or your average velocity. for the molecule within a substance. So this depends on the element or compound, or basically the substance, and then it depends on the temperature. Right? So each substance is going to have a different graph because of its different masses and its different makeup. Each one's going to have a different temperature that it ends up being at the highest point. Right, so if we want to calculate the RMS speed of helium atoms near the surface of the sun at a temperature of about 600 K. So root mean squared equals square root of 3 times 1.38 times 10 to the negative 23rd times 6,000. And then we have to get this mass of the helium. Well, one helium has 2 protons and 2 neutrons. And we're not going to worry about the electrons here. They're so small that we don't have to worry about them. And so you have 4 different units. So you're 4 times the 1.67 times 10 to the negative 23rd. Okay. This is important to do it this way because we need our mass in kilograms because we're dealing with a meters per second. So we need that kilograms here. Alright, so when we plug this into a calculator, we get 3, I'll clear this, 3 times 1.38 times 10 to the negative 23rd times 6,000 divided by 4 divided by 1.67 times 10 to negative 27. Right? And then take the square root. So square root of that answer. And we get 6,098. I want to make sure. Alright. Alright, so, and that would be meters per second. And so that's going to be your root mean square for this. Alright, so the next thing is when we start looking at change of phases. And so when you have a solid and you increase the temperature, it starts to warm up. It starts to get enough energy that the bonds are breaking and becomes a liquid. And then as it warms up even more, it starts to have enough energy for the molecules to break the surface and become a gas. And so we have this diagram here because it's not just the temperature but also the pressure that will kind of determine when a substance goes from a solid to a liquid to a vapor or gas. And so the triple point, and this is the temperature and pressure that will allow all 3 substances to exist in equilibrium. Okay, and this is per substance. So this is like, let's say water for one, or we can have another substance like iron for another and have a different graph. But it's going to look very similar. You're going to have a triple point. So along this line, you are either going to be a solid or a vapor, or you'll be going past, from solid to vapor and vice versa. And we call this sublimation and dissociation or something like that. I forget. It's not as common as everything else. I know it starts with a D. Just can't think of it off the top of my head. Let me see if I say it in the next one. No, I don't. Okay. Anyways, right along this line, you're going from a solid to a liquid, so this is melting and freezing. Along this line, liquid to a vapor, so it's evaporation and condensation. When you hit this critical point, anything behind this cannot change, or I should say anything above this. Gases cannot change into a liquid. So there is no, this line basically stops at any temperature above this temperature. So anywhere over here is going to be a gas. There's no way of going back to a liquid. This pretty much just stops right here. And that's the critical point. Right? Regardless of how much pressure you are in. So if you have a liquid here, and let's say this liquid is still above the melting, the boiling point, you could still force it to become a liquid by applying enough pressure, or vice versa. You can force the liquid to become a vapor if it's below the boiling point by applying so much pressure. But when you're beyond this critical point, that's not going to happen. There's not a single amount of pressure you can apply that would make this become a gas. This critical point does depend on the gas, and when a substance is below its critical point, it is considered a vapor. Even though we kind of use vapor and gas interchangeably a lot of times. And then at low pressures, a solid changes directly into a vapor, and again, we call this sublimation. All right, so with evaporation, this is where vaporization below the boiling point happens, and so you get a liquid becoming a gas below the boiling point. The liquid molecules are capable to move around. These molecules will move at different speeds, and some of the speeds are faster than others, and some are slower than others, and they will collide with each other, and when they collide, they're exchanging kinetic energy, and so some molecules build up enough energy to break the surface and start becoming a vapor, and you start having vaporization. When that happens, those molecules that leave the surface will have that kinetic energy with them, and will cause the temperature of the liquid itself to decrease, right? Because they are leaving that surface, which causes that's like when you get out of the shower and the water is evaporating off of you. It causes your body temperature to decrease because you're losing energy as it's going into the air. Condensation, the molecules are close to the surface, they are attracted to the liquid, and the molecules will collide with the liquid at times, and they will start to become part of the surface by striking the surface with a higher kinetic energy. And when they do that, the kinetic energy of the molecules is given to the liquid, and so the temperature of the liquid will actually increase. Okay, kind of opposite what I just said with the evaporation. When these two things are happening simultaneously, you're having condensation happen and you're having evaporization happen. Right? They may happen at different rates. When they reach the point where they've kind of happened at the same rate, this is what we call saturation. Means the number of molecules condensing is equal to the number of molecules evaporating, which means you can't have any more molecules up in this area above it. That's considered saturated. The pressure at this point is considered what we call the vapor pressure. And this vapor pressure will be related to temperature, and it increases with temperature as well. Right, the last thing is boiling. This is vaporization at the boiling point. And this is when the vapor pressure equals the external pressure on the outside. And then the substance will begin to boil, and that's always a specific temperature given a material. So water is 212 degrees Fahrenheit, 100 degrees Celsius. Higher altitudes changes the air pressure. You get less air pressure, which means vapor pressure can occur at a lower value. And so the material will start to boil at a lower value. It's something to know if you ever go to Denver. Alright, so that's the end of kinetic theory. The next chapter is going to be heat, and then the last chapter will be, whoops, didn't mean to do that, will be thermodynamics. And then that will be the end of physics 1. If you have any questions, email me, of course. And I will try to get back to them as possible. You can always find any way to ask me a question. I'm fine with questions. I like looking at this stuff and doing this stuff, so I'm not bothered at all about it. Alright, I'll see you next video.